Good morning, good morning, good morning. So you guys are good with the check equals false part of LU now and all of this stuff? Yeah, Julia has his quirks, but I think the positives, the speed, and it's an elegant language outweigh that, but you may have a different opinion. That's fine. I just want to caution everybody, the cases are going up in the state of Michigan, so let's don't let our guard down. Just keep it up, keep it up. We've kept the university open. That's a very good thing. Okay, we're still up in the clouds a little bit today, but we're going to start descending, and then next week we're back to firm ground. I think you guys will love it when we start doing orthogonal vectors and Graham-Schmidt. I honestly believe that. Okay, so we're working on our abstract vocabulary. We've done span of a set was the most recent one. So you take any subset of Rn and you close it up by taking linear combinations. That's the span. So you're working with the set, you're checking if it's a subspace. Nope. It doesn't have this particular linear combination, so you throw that in, and then you take more linear combinations until you can't generate any new vectors. That's the span. So it's just a way of turning any set into a subspace. Let's note that if S was already a subspace, and then you take the linear combinations of it, it's already closed under it, so the span of a subspace is just the subspace. You don't get anything new. So that's the span, just a way of representing a subspace. And we'll see it's a very convenient way to give us, in Rn, finite ways to represent a subspace. So a vector x in Rn is in the span of a set S if I can find some k, I find a bunch of vectors that are in S, I find coefficients that are in the reals, and I do their linear combination, and I get x. And in principle, k is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, up to infinity, but that's the definition. We applied this to a matrix. We often look at the columns of a matrix, look at the rows for doing multiplication, etc. Here we're doing columns. The column span of A, you view the columns as vectors in Rn, and so you just do the span of the columns. So it's all linear combinations of the columns of A. So that gives you a subspace of Rn. We already had an interesting subspace associated with a matrix. We called that the range. So the range was all vectors y in Rn that I can generate as the form A times x. And then we had this other subspace lying around, which is the null space of A, where you look at all vectors in Rm that get mapped into 0 when you do A. Okay, so range, all vectors I can write as A times x, and null, all vectors that get mapped into the 0 vector. So it's the 0 space of A. And today we're going to get all these things and tie them all up together. Okay, so I actually had notes. So let's prove that the range of A is equal to the column span of A. So why do we suspect that is true? So what are the facts we have lying around? We have AX equals B has a solution if and only if B is a linear combination of the columns of A. Okay, so that was our chapter 7 way for having existence of solutions to an equation. Okay, so that's fact 1. We have another condition was AX equals B has a solution, and I'll write it if and only if with the double arrow. B was in the range of A. Then the last one we have was AX equals B has a solution if and only if B is in the column span of A. So that's really just a restatement of the first one. So we suspect that these two things that have different names are actually the same, okay? They must be. They're giving us the same if and only if condition on solution, so they must be the same thing. Yep?
So is the column span the linear combination of the subsets of the column or all of the columns?
Okay. So the question in chat was, is the column span the span of a subset of the columns of A or all of the columns? So you take all of the columns. So A has m columns if it's n rows and m columns. Now it could be that some vector here is a linear combination of the other one, so it's redundant, but it's still in the span of the columns of A. So you take all of the columns. Okay? And then both those two formats are comparable. Oops, I guess I don't understand that one. But
He meant like just the combination of A1 and A2, that will also be in the span, and then linear combination of all of them will also be in the span.
oh, okay. Yeah, so a vector in here would be 2 times the first column plus 3 times the second column minus 17 times the third column. We ignore the fourth and fifth column, and then we put zeros in it, and then we put square root of 2 times the last column. That would be an example linear combination. So you could generate all possible things, okay? And then why did we have that AX equals B has a solution if and only if B is in the range of A? Well, remember the range of A is all things that look like AX for some X in Rn. So if B isn't in here, then there's no X such that AX equals B. So that's why that was true. And then our early thing, just by writing down what A times X was that AX equals B has a solution if B can be written as a linear combination of the columns. And that means it has to lie in the span because the span is all possible linear combinations. Okay, so we have these things. We suspect range of A is equal to that, so let's just check. So let's do A. Once again, we write it as A1 column, A2 column, AM column. And I'm going to do this as AX, so I apologize. I can do that easier than you can with your notes. And I'll write this as X1, X2, XM. So that's A times X. Okay, so using our column times row definition of matrix times matrix multiplication, because this is just an M by 1 matrix, we take this column times this row plus this column times this row, dot, 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 this column times this row. So we just write that down, and we get, and I'll put the constant out front, xm am column. Okay, so A times X is always a linear combination of the columns of A. Okay, so it's really just us getting our definitions down again. And so we write range of A, so that's all things that look like AX, where X is an arbitrary thing in our M. A is n rows and m columns. And from the above, we see this is everything that looks like x1, a1 column plus x2, a2 column, dot, 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 xm, am column, such that x1 is a real number, x2 is a real number, xm is a real number. And I'll stop here and let you catch up. Okay, so recognizing A times X as a linear combination of the columns, that is super, 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 super key. So I hope that works for you. Now, when we write linear combinations, we often prefer to have things that look like numbers. So I'll just rewrite this, even though I don't have to. But I'll just rewrite it so that it looks like the numbers we typically use when we do linear combinations. Okay, and I'll just shortcut a little bit and just say the alpha i's are in the reals instead of writing down alpha 1, alpha 2, alpha m. But this is, since the alphas are free, this generates all possible linear combinations of the columns of A, and then by definition, that's the span. Come on. Let's write A2 column, comma, dot, 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 AM column. So we take all the linear combinations of the columns of A. That's the span of those vectors. And then that was what we called the column span of A. So it's true. Those two things are the same. They're just different ways of writing down the same object. And really what it was just an exercise in applying the definitions and then writing down, once again, this being equal to this. They look very different, but it's how you relate what does A times X look like and why is that the column span of A. Works, kind of? Okay, so that's how we use spans. So spans help us to generate subspaces. Okay, so it's just more compact notation. I could have just written down, we could always just said range of A is the set of all possible linear combinations of A, but that's wordy. So span is just this compact notation that does the same thing. So spans help us take, in this case, it's really important, we have M elements in this set, and we generate a subspace just by saying we take all possible linear combinations. So it's a way to associate something that has an infinite number of elements, and these guys are generators of that. Okay, so that's the way to think about it, is generating this infinite set with infinite number of elements just by using these as generators. So a basis takes this one step further. Okay. It's the smallest set of vectors that span a given subspace. The smallest set. And we'll just go back to column span, and really one of the questions that was asked is, do you just use some of the columns of A or all of the columns of A? Well, if this column were a linear combination of the previous ones, we could just throw it away and generate the same span with a smaller set. We could look at the next one. Well, it's not a linear combination. The next one is, it is a linear combination. So we could get it down to where we take a set of linearly independent vectors that generate that span by throwing away all of the dependent vectors. And that's what a basis does. It's the smallest set of vectors that span a given set. So let's define basis and dimension. So definition. Suppose that V is a subspace of Rn. Okay. Then a set of vectors V1, V2, up to Vk is a basis of V if, and we have two things holding true. We want this set to be linearly independent. And there have to be enough vectors that we generate everything in V by taking linear combinations. So the span of V1, V2, Vk equals all of V. Okay, so I like to think of this as like a Goldilocks thing, okay? The porridge is not too hot and it's not too cold, okay? What do I mean by that? It's not too big, so it's small enough to be linearly independent. Or throw in extra vectors, it becomes dependent. So that's the Goldilocks thing. It's just small, it's small enough that it's linearly independent, yet it's big enough that I can generate everything in V. Okay? So if you have that concept, it's easy to remember what these things are, these little mnemonics, okay? Small enough to be linearly independent. And big enough to generate everything in V. So that's kind of a really amazing property. The vectors are linearly independent. There's nothing redundant in it. And yet by taking their linear combinations, I recover my subspace completely. So this is like the minimal and best description of a subspace. And if I'm in a computer, I don't carry around every vector in the subspace with me. I carry around a basis, okay? Because I can generate everything here by just some linear combination. So I just work with the basis. That's the whole idea. It reduces this great big set to just a finite list of vectors. Okay, and then I need to define dimension, make it stand out, okay. The dimension of V is K, the number of elements in a basis. Okay. It's not too big and it's not too small. That's a basis. And the exact number of elements you need to do that is called the dimension. So guess what? Rn, what do you think its dimension is? N. Okay? And we'll see that. Okay? So let's see if Rn is an n-dimensional vector space. Do we have basis vectors lying around for Rn? So let's just check that. Example. So let's let In be the n by n identity matrix. And EI is the ith column. So E1 is just 1, 0, dot, 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 0. And then En 0, dot, 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 0, 1, okay? And EI is zeros, I and a 1 in the ith spot, and then the rest of them are zeros, okay? So we claim that these guys form a basis. Okay, so here's our code word in Rob 501 for the word proof. Okay, if you want to show something's a basis, it has two properties. The elements need to be linearly independent, and we need to be able to generate every possible vector in Rn by a linear combination. So it's almost a one-liner, okay? So let's just write X in terms of its components. Okay, can we write X as a linear combination of those guys? Yeah, I can do X. Let me be more explicit. Oops, I forgot XM. XM gives you guys a chance to catch up. Then I got rid of the plus sign. There's a 1 down here. Okay, so that's x1 e1 plus x2 e2 dot 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 xm em. That's cool. Okay, so I took an arbitrary point in Rn, and then I turned the n into an m. Took an arbitrary point in Rn, and I wrote it as a linear combination of these. So that shows that the span of that set, the set is big enough is all of Rn. Now, are those vectors linearly independent? Then it'll be a basis, okay? Now, so we need to check linear independence. But 0, 0, 0 equals alpha 1 E1 plus alpha 2 E2 plus dot 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 alpha n En. The only way to do that is if we take all of the coefficients equal to 0, okay? So if any of them is not 0, we don't get the 0 vector. So that's linear independence. Okay, so conclusion basis, check, and then the dimension of Rn. It would have been funny if it was 2n, right? It would have been funny if it was n minus 4, but the dimension of Rn is n. Yep, it's an n-dimensional vector space. Okay, so that's one basis lying around for Rn. Is there questions on why the vectors E1, E2, En form a basis? That seems almost intuitive. Yeah, so there's one basis. Are there lots of bases for Rn lying around? It's kind of our next question. Or there's only one type of basis, okay? So that's a basis for Rn. Here's another claim. Let A be an n by n matrix. Whoops. With determinant of A not equal to 0. So it's square, we can take its determinant. Then the columns of A form a basis of Rn. Ooh. Okay, I just want to go back and check what we just did up here. This is an n by n matrix. And these are its columns. And we said the columns of the identity matrix form a basis of Rn. Okay, so this is a generalization of that. Let's just see why it's true. So this one, when it's the identity matrix, finding the coefficients, so I could write a general X as a linear combination. That wasn't very hard. It's the identity matrix, okay? And then proving linear independence wasn't very hard either. So it's going to be a little bit different, but we're going to use facts that we know about solutions of linear equations. So it's the same proof. Okay. So let's have some notation. So you guys are so used. And it's n by n, okay? I'm always wanting to do a n by m, but m is n, okay? So we write this. Okay? And then what we're looking at is the set of vectors A1 column, A2 column, AN column. Okay, so we extract out the columns, we get vectors in Rn, and we want to know, is that a basis? Okay. Well, let's first check linear independence. So we write down a linear combination. Can't change alpha to A, should stay consistent. And we set it equal to the n by 1, 0 vector. We want to know, are there any non-trivial solutions? Well, this is equivalent to me writing, and I'll put the matrix back together, but Okay, linear combinations and matrix equations, those are the same things, okay? Just always get used to it. Whatever vectors you put here, you just stick them in as the columns of the matrix. The coefficients out front become the things on the right-hand side. Those are the same things, okay? And so this has non-trivial solutions if and only if. So this is A, we'll call that alpha, if and only if A alpha equals the zero vector in Rn. Now, our assumption on A is that its determinant is non-zero. So why can we conclude that their only solution to this equation is alpha 1 equals 0, alpha 2 equals 0, alpha n equals 0? Well, we know our necessary and sufficient condition for AX equals B to have a solution and it be unique is determinant of A not equal to 0. Okay, B just happens to be 0, that's fine. So alpha equals 0 is always a solution, but if it's unique, then that's the only solution, etc. Okay, so determinant of A not equals to 0 implies alpha equals 0 n minus 1 is the only solution. That's by uniqueness. And that's the definition of linear independence, okay? Conclusion. Columns of A are linearly independent. Okay, vectors are linearly independent if the only way you get the zero vector when you add them up with a linear combination is with the trivial coefficients, all of them being 0. And that's what we just showed. A alpha has a unique solution, so and alpha equals 0 is one solution, so that's it. Okay, how about the span part? So what do we want to do? We want to take an arbitrary vector in Rn and find coefficients that we write that vector as a linear combination of the columns. So I'm going to do us a favor, and I'm going to let B in Rn be an arbitrary vector. Okay. We seek coefficients, alpha 1, alpha n, such that we can write B equals alpha 1, A1 column, alpha 2, A2 column, dot, 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 alpha n, A-n column. Why? Because that's the definition of something being in the span. Okay. So I just rewrite this as A1 column, A2 column, AN column, alpha 1, alpha 2, dot, 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 alpha n. And guess what? I'm going to swap my B to the other side of the equation. This is my matrix A again. This is my vector alpha, and then that's B. So this is if and only if A alpha equals B. So does there exist alpha in Rn such that A times alpha equals B? And the answer is yes, because determinant of A not equal to 0 implies there exists a solution. We don't care about uniqueness here. Implies we've checked the span property. Check. Okay, so the span is all of Rn. Make sense? Now, I just want to ask you honestly, when you looked at this definition, I mean, it's kind of cool, smallest set of vectors that allow you to generate everything in a given subspace. We just did easy subspaces, the Rn itself. But did it look like you were solving linear equations there? Not really, okay, but you find out as soon as you're checking linear independence and as soon as you're checking span, it's exactly equivalent to solutions of linear equations, okay? So linear algebra, these abstract concepts, they're all tied to really setting up linear equations. Okay, so there's lots and lots of bases to Rn lying around. You take any matrix whose determinant is non-zero, any square matrix, determinant's non-zero, you generate bases for Rn and vice versa, you get that. Cool. Okay, so this is more compact notation is what really this is, rank and nullity of a matrix. So let's let A be our infamous rectangular matrix, okay, n by m. Definition. A. The rank of a matrix is defined to be the dimension of the range of A. And nullity, the zero-ness of A, is the dimension of the null space of A. Now I'm going to see if I can force you to say something, okay? Everybody online? I'm going to see if I can get you to say something too. I've got my speaker turned on. Oh, it turned itself off because nobody's using it. Okay. Dimension of the range of A. Remember, the range of A, that's the same thing as the column span. Okay, where column span. Range of A is the column span. The rank of A is the dimension of the column span. So what is the rank of a matrix in terms of we kept saying over and over again, we had this method for counting something, remember? What were we counting when we were looking at uniqueness of solutions of AX equals B and existence of solutions? Somebody, I'm going to have to call on Tribby here in a moment, and she doesn't want to do that, okay? Yes. It's the number of linearly in the answer given by the class from the front row student, but just by chance, because that's probably as far back as I can hear with my bad hearing. The rank of A is just a number of linearly independent columns. And remember, our pro tip was helping us see if the columns were linearly independent or not, and our semi-pro tip was we do A transpose A, we look at the diagonal of U, and the number of non-zero elements is almost exactly equal to the number of linearly independent columns of A, and then we'd look at the rows of U to make sure that that was true, okay? So this is just giving a definition to this thing. We spent so much time talking about this number, okay? So rank of A is not anything super novel. We were using this concept before we had the vocabulary to say it's a number of linearly independent columns of A. So it's just vocabulary, but it's a really interesting vocabulary because we look at the span, the dimensions. So the rank of A is just number of linear and independent columns. And the nullity of A is just a number of linearly independent vectors that A wipes out when you apply it to them, okay? So we're just counting the dimension of that. So it's very, almost physical. Okay, so once we have these, image, file, ta-da, open up, facts and nullity, and rank. Out of the way. Ooh, gotta shrink it a little bit, sorry. Ooh. Get out of the way. Okay, so here's, you guys can almost see that. At home, they can see it better. When you get to the homework on this chapter, I'm going to have you, for several matrices, calculate, or stay put. I'm going to have you calculate the number of linearly independent vectors in the columns of A. I want to have you calculate the number of linearly independent vectors that A wipes out, the null space. Well, they're related. The rank plus the nullity is always equal to the number of columns of the matrix, okay? So the number of dependent vectors, that's the number of ways you can get non-unique solutions. That's exactly how you get linear combinations, non-trivial linear combinations that add up to 0, okay? So it's a really cool thing. This was our pro tip. Essentially, we were trying to get whether the columns of A are linearly independent. We looked at A transpose A. And then when we were just trying to count the number of linearly independent columns of A, we looked at this and we did the LU factorization. We looked at the diagonal of U. Oh, I'm out of time, but we'll have to come back to this because there's so much richness in this. But this is cool. The rank of a matrix and its transpose, they're exactly the same. We'll talk about that, and then we'll get started on geometry on Monday. So this is getting us back down to earth. Yeah, it went by quickly, our 50 minutes. I apologize. I wish I could just go, boom. Now we've got another 20, but we don't. And Monday we'll start with this again, and then we'll start on orthogonal vectors, geometry, and things like that. So thank you guys, and have a great weekend, and be safe.